Welcome to LLM Architecture Deep Dive, Mathematical Foundations for Data Scientists. If you've been using large language models like GPT or BERT as black boxes, this course will change that forever. As a data scientist, you know that true innovation happens when you understand the mechanics beneath the surface. Today, we're unlocking the mathematical secrets that power modern AI. We'll deconstruct the transformer architecture that drives ChatGPT, Claude, and every major LLM you've encountered. By the end of this journey, you'll understand the precise mathematical transformations that convert raw text into intelligent responses. You'll grasp the attention mechanism that revolutionized AI, the embedding strategies that capture meaning, and the neural architectures that enable reasoning. This isn't just theory. It's the foundation you need to conduct cutting-edge Gen AI research, modify existing models, and build the next generation of AI systems. Ready to move from user to creator? Let's begin. Here's our roadmap to transformer mastery using the SCQA framework. We face a situation. LLMs are incredibly powerful, but their inner workings remain opaque to most data scientists. The complication? True innovation in AI requires deep understanding, not just API calls. This raises a critical question. How do we decode the mathematics that makes these models work? Our answer lies in systematically dissecting the architecture into four fundamental stages. Module 1 covers input processing, how raw text becomes mathematical tensors through tokenization, embeddings, and positional encoding. Module 2 reveals the attention mechanism, the revolutionary query, key, value system that allows models to understand context and relationships. Module 3 explores the transformer block, how attention combines with feed-forward networks, residual connections, and layer normalization to create deep, trainable architectures. Finally, Module 4 examines output generation, the mathematical process that converts internal representations back into human-readable text through linear projections and softmax functions. Each module builds upon the previous, creating a complete understanding of how text flows through an LLM from input to output. Let's begin our journey into the LLM by understanding a fundamental constraint. These models don't actually understand language the way humans do. At their core, LLMs are mathematical machines operating on vectors, matrices, and numerical computations. When you type, "Hello, how are you?" the model doesn't see letters or words, it sees arrays of numbers. This creates our first challenge. How do we bridge the gap between human language and machine mathematics? The answer lies in a sophisticated three-step transformation process. First, we break text into manageable pieces through tokenization. Then, we convert these pieces into meaningful numerical vectors through embeddings. Finally, we add positional information so the model understands word order. This module reveals exactly how this linguistic alchemy works, transforming the seemingly impossible task of teaching mathematics to understand meaning. Every LLM from GPT to BERT begins with this same fundamental process. Tokenization is the first step in our transformation process, breaking down text into the vocabulary units that the model can understand. Think of it as creating a dictionary where every possible word piece gets a unique number. Modern LLMs don't use whole words, they use subword tokenization algorithms like byte pair encoding or word piece. Here's why. The word understanding might be split into under and in standing. This approach handles rare words, typos, and even languages the model hasn't seen before. Let's see this in action. The sentence, "Data scientists analyze patterns," might become tokens 1534, 89 bunt, ton, 2847, 9432. Each number corresponds to a subword in the model's vocabulary. GPT-4 has a vocabulary of roughly 100,000 tokens, while earlier models used 50,000. The tokenizer learns these splits during training by finding the most frequent character combinations. This is crucial for data scientists because tokenization affects model behavior. Longer sequences cost more to process, and unfamiliar terms might be split into many tokens, reducing context window efficiency. Understanding tokenization helps you optimize prompts, estimate costs, and debug unexpected model responses. It's also why some models struggle with certain tasks like counting characters or reversing words. They're not saying individual letters but abstract token units. Now we have integer tokens, but integers alone carry no meaning token. 1534 could represent anything. This is where the embedding layer performs its magic, transforming these meaningless numbers into rich, high-dimensional vectors that capture semantic relationships. Think of embeddings as coordinates in a vast meaning space. The word king might be represented as 0. 0.2, 0. 0.1, 0. 0.8 in a 768 dimensional space, while queen has coordinates 0. 0.3, 0. 0.7. Notice how similar they are. That's not coincidence. It's learned semantic similarity. During training, the model learns that words appearing in similar contexts should have similar vector representations. This creates fascinating mathematical relationships. The vector from man to woman is remarkably similar to the vector from king to queen. These embeddings typically have dimensions ranging from 512 in smaller models to 12 to 288 in GPT-4. Each dimension captures different aspects of meaning. Some might encode gender, others might capture abstract concepts like royalty or profession. For data scientists, this embedding space is where transfer learning happens. Pre-trained embeddings capture years of language understanding, which is why fine-tuning works so effectively. The embedding layer is also where most of a model's parameters live. In GPT-3, roughly 50% of the 75 billion parameters are in the embedding matrices. We now have meaningful vectors, but we've lost something crucial: order. Unlike RNNs that process sequences step by step, transformers see all tokens simultaneously. This parallel processing is what makes them fast and powerful, but it creates a fundamental problem. Consider these sentences: man bites dog versus dog bites man. To a transformer without positional information, these would be identical, just the same three embedding vectors in a set. The model would have no way to distinguish between them, making it impossible to understand syntax, grammar, or narrative flow. This is the order problem, and it's not just academic. Word order carries critical meaning in most languages. Not good means something very different from good not. For data scientists working with transformers, understanding this limitation is crucial because it explains why positional encoding isn't optional. It's absolutely essential. Without it, even the most sophisticated attention mechanisms would fail to capture the sequential nature of language that humans take for granted. The solution to our order problem is elegant positional encoding. We create a unique mathematical signature for each position in the sequence and add it directly to the token embeddings. Think of it as giving each word a timestamp that the model can use to understand sequence order. Here's the key insight. The positional encoding vector has the same dimensions as the embedding vector, so we can simply add them together. Position 1 gets one signature, position 2 gets a different signature, and so on. This addition doesn't overwrite the semantic meaning, it enhances it with positional context. The beauty lies in the mathematical properties of the encoding scheme. It needs to be deterministic. Same position always gets the same encoding. Unique, no two positions share the same signature, and bounded values don't grow infinitely large. For data scientists, this means the model can distinguish between the cat sat on the mat and the mat sat on the cat while preserving all the semantic richness of the individual word embeddings. The positional encoding essentially teaches the model that meaning comes not just from what words are present, but from how they are arranged. This simple addition operation bridges the gap between semantic understanding and syntactic structure. Now, for the mathematical implementation, the sinusoidal positional encoding formulas that create these unique signatures. For even numbered dimensions, we use PE-pose, 2i's, and pose IC 1000 2IC dot model. For odd numbered dimensions, PE pose 2e plus 1c, cos pose 1000 2e 2e dub model. Let's decode this formula. Pose is the position in the sequence. 0 for the first token, 1 for the second, and so on. I represents the dimension index, and buttons is the total embedding dimension, typically 512 or 768. The magic is in the 1000 base and the varying frequencies. Different dimensions oscillate at different rates. Some change rapidly with position, others change slowly. This creates a unique fingerprint for each position that never repeats. Why sine and cosine? They are bounded between point 1 and 1, preventing the values from exploding. They're also periodic and smooth, which helps the model interpolate between positions it has seen during training. For data scientists, this formula has practical implications. The model can theoretically handle sequences longer than those seen during training because the mathematical pattern continues. However, very long sequences may still challenge the model because the attention computation grows quadratically with sequence length. Understanding this formula helps you debug position-related issues and optimize sequence lengths for your specific applications. Our input tensors are now mathematically prepared, tokenized, embedded, and position encoded. But having meaningful vectors in the right order is just the beginning. The real magic happens next. How does the model actually understand relationships between words? How does it know that the animal didn't cross the street because it was too tired refers to animal and not street? This is where we enter the revolutionary core of transformer architectures, the self-attention mechanism. This module represents the mathematical breakthrough that changed everything in AI. Before attention, models struggled with long-range dependencies and context. After attention, we got GPT, BERT, and the entire modern AI revolution. We are about to explore the most important equation in modern machine learning. This isn't just another neural network component, it's the innovation that made large language models possible. Ready to understand the mathematics that powers every conversation with ChatGPT? Let's start with the intuition behind self-attention. Imagine every word in a sentence having a conversation with every other word, asking how relevant are you to understanding my meaning. Self-attention is precisely this, a mathematical mechanism where each word looks at all other words in the sequence to determine which ones are most important for its own representation. Consider our earlier example. The animal didn't cross the street because it was too tired. When processing the word it, the model needs to figure out what it refers to. Self-attention allows it to look at both animal and street and compute relevant scores. In this case, animals would receive a much higher attention score than street because the context suggests that animals, not streets, get tired. This isn't programmed. It's learned from patterns in training data. The beauty is that this happens simultaneously for every word with every other word, creating a rich web of contextual understanding that captures both local syntax and long-range semantic relationships. To implement this relevance scoring mathematically, attention transforms each input embedding into three specialized vectors: query, key, and value. Think of these as different roles a word can play in the attention conversation. The query represents what I'm looking for. It's the current word asking questions about context. The key represents what I contain. It's how each word presents itself to be queried. The value represents what I will contribute. It's the actual information that will be passed forward. Here's a concrete analogy. Imagine you're in a library looking for information about machine learning. Your query is machine learning concepts. Each book has a key, its title, and summary that describes what it contains. When your query matches a book's key well, you decide to read that book's value, its actual content. In attention, the word it has a query vector asking what noun should I refer to. The words animal and street each have key vectors describing their properties. The query key similarity determines attention weights, and these weights are used to combine the value vectors. This QKV structure is what makes attention both flexible and powerful. The same word can simultaneously query others while being queried itself. The Q, K, and V vectors aren't magic. They're learned projections of the input embeddings. For each embedding vector X, we compute three transformations using learned weight matrices. The formulas are elegantly simple: Qx in SVLGQ, Kx in SVLGK, and Vx in SVLGV. These weight matrices, VACO, and VAFO, are parameters that the model learns during training. Think of them as specialized lenses that extract different aspects of each word's meaning. The query matrix WQ learns to extract what this word needs to know about context. The key matrix YK learns to extract how this word should present itself to others. The value matrix WV learns to extract what information this word should contribute. Crucially, these matrices are shared across all positions in the sequence. The same but key transforms every word's embedding into its query vector. This sharing is what allows the model to generalize patterns across different sentence positions. For data scientists, understanding this parameterization is key. These matrices contain the learned knowledge about language relationships. When you fine-tune a model, you're primarily updating these attention weights to capture domain-specific patterns. The dimensions typically match the embedding size. If embeddings are 768 dimensional, each QKV vector is also 768 dimensional, though multi-head attention often uses smaller projections. With our QK and V vectors ready, we can now compute attention through a three-step mathematical process. Step 1. Calculate similarity scores between the query of the current word and the key of every word in the sequence. This is done using the dot product, a measure of vector similarity. High dot products indicate strong alignment between what a word is seeking and what another word offers. Step 2. Scale these raw scores and apply the softmax function to convert them into a probability distribution. This ensures all attention weights sum to 1.0, creating a normalized measure of relevance. Step 3. Use these attention weights to compute a weighted average of all value vectors. The result is a new representation of the current word that incorporates contextual information from the entire sequence. This process happens simultaneously for every word, creating a rich matrix of interword relationships. For data scientists, this three-step flow similarity, normalization, aggregation is the computational heart of every transformer model. Understanding this flow helps you debug attention patterns, interpret model behavior, and optimize attention mechanisms for specific tasks. Here is the equation that powers modern AI. Attention QKVC softmax, QKKPCC, CKPC, CCCCC. This single formula encapsulates everything we've discussed. Let's deconstruct each component. QIEnc. KT computes the dot product between every query and every key, creating a matrix of similarity scores. The transpose operation ensures proper matrix dimensions. We're comparing each query against all keys. Next, we divide by doc, where doc is the dimension of the key vectors. This scaling factor is crucial for numerical stability. Without it, the dot products grow large as dimensions increase, pushing the softmax function into saturation regions where gradients vanish. The decascaling keeps the variance of the dot products constant regardless of dimensionality. The softmax function then converts these scaled scores into a probability distribution across all positions. Each row sums to 1.0, representing how much attention each query pays to each key. Finally, we multiply by V to compute the weighted sum of value vectors. For data scientists, this formula is more than mathematics. It's the innovation that made modern NLP possible. Every breakthrough from BERT to GPT-4 relies on this scaled dot product attention. Understanding each component helps you modify attention mechanisms, debug model behavior, and design custom architectures for specific tasks. Let's visualize what attention actually produces. Imagine a heat map where rows represent words asking questions and columns represent words providing answers. The intensity of each cell shows the attention weight, how much the row word focuses on the column word. Consider the sentence. The robot picked up the ball because it was heavy. When we process the word it, we get a row in our attention matrix. The it row would show high attention weights for balls, bright color, and low weights for robots, dim color, because context suggests that balls, not robots, are typically described as heavy. This isn't programmed, it's learned from thousands of examples where pronouns refer to appropriate nouns. Different attention heads learn different types of relationships. One head might specialize in syntactic dependencies, subject-verb relationships, another in semantic similarities, synonyms, and related concepts, and another in discourse structure, anaphora resolution like our its example. For data scientists, these visualizations are powerful debugging tools. When your model makes unexpected predictions, examining attention patterns can reveal whether it's focusing on relevant context or being distracted by irrelevant information. Tools like BirdFace make these attention patterns easily interpretable, turning the black box into a transparent reasoning process. A single attention mechanism is powerful, but we can make it even better through multi-head attention. Instead of having one set of what QQ, RQ, and VXCV matrices, we create multiple heads, each with its own learned projection matrices. Think of it as having multiple specialists examining the same text simultaneously. Head 1 might specialize in syntactic relationships, learning to connect subjects with verbs. Head 2 might focus on semantic similarities, linking synonyms and related concepts. Head 3 might handle long-range dependencies, connecting pronouns with their antecedents across many words. Each head operates independently, computing its own attention rates and producing its own output. These outputs are then concatenated and passed through a final linear transformation to combine the insights. The mathematical formula becomes multi-head Q, KVT concat, head D, head D, YDO, where each head IDT on, attention, YD, ID, VD. Typically, models use 8, 12, or 16 heads. GPT-3 uses 6 heads in its largest layers. For data scientists, multi-head attention is crucial because different NLP tasks benefit from different types of relationships. Machine translation needs syntactic understanding, sentiment analysis needs semantic relationships, and question answering needs long-range reasoning. Multi-head attention captures all these patterns simultaneously, making transformers remarkably versatile. We've mastered the attention mechanism, the revolutionary heart of transformers. But attention alone doesn't make a complete model. Think of attention as a powerful engine, but engines need chassis, transmission, and control systems to become functional vehicles. That's exactly what we are building now, the complete transformer block that houses our attention mechanism. These blocks are the fundamental building units that, when stacked dozens of times, create the deep networks of GPT-4, Claude, and other modern LLMs. Each block takes the output of the previous block, processes it through attention and other components, then passes enhanced representations to the next block. By the end of this module, you'll understand not just how attention works, but how it integrates with feed-forward networks, residual connections, and layer normalization to create trainable, stable, and powerful deep architectures. This is where we transition from understanding individual components to seeing the complete engineering marvel that enables modern AI. Before we examine other components, we need to solve a fundamental problem in deep learning, the vanishing gradient problem. In very deep networks, and modern LLMs have 96 plus layers, gradients can shrink exponentially as they propagate backward through the network during training. By the time gradients reach early layers, they're essentially zero, making learning impossible. The solution is elegantly simple: residual connections, also called skip connections. Instead of just passing the output of a layer forward, we add the input to the output layer x plus x. This creates an information highways that allows gradients to flow directly through the network, bypassing the layers that might diminish them. Think of it as providing an express lane alongside the local roads. Even if the local processing, the layer, reduces the signal, the express lane, the residual connection, ensures the original information gets through. For data scientists, this is why we can train models with hundreds of layers. Without residual connections, we'd be limited to shallow networks that couldn't capture the complex patterns needed for language understanding. The mathematical beauty is in its simplicity. just addition, but the impact is profound. Every major deep learning breakthrough since 2015, from ResNet to transformers, relies on this principle. Residual connections help gradients flow, but we also need to stabilize the actual values flowing through the network. This is where layer normalization comes in. During training, the inputs to each layer can vary dramatically in scale and distribution, making learning unstable and slow. Layer normalization solves this by normalizing the outputs of each layer to have zero mean and unit variance. Here's how it works. For each sample in the batch, it computes the mean and standard deviation across all features, then normalizes each feature by subtracting the mean and dividing by the standard deviation. Unlike batch normalization, which normalizes across the batch dimension, layer normalization operates on individual samples. This makes it particularly well suited for sequence models where batch sizes might vary and sequence lengths differ. The normalization is followed by learnable scale and shift parameters that allow the model to recover the original distribution if needed. For data scientists, layer normalization is crucial for training stability. It reduces sensitivity to weight initialization, speeds up convergence, and makes the training process more robust to hyperparameter choices. In transformers, layer normalization is applied after both the attention sublayer and the feed-forward sublayer, ensuring stable information flow throughout the deep network. After attention contextualizes the tokens, we need another component to process each token's information individually, the position-wise feed-forward network, FEV. This is a simple but crucial two-layer fully connected neural network applied independently to each position in the sequence. The FFN structure follows a specific pattern: expand, activate, contract. The mathematical formula is FFNX max max, number 0 x value. Let's break this down. XW plus BR expands the input from the model dimension, typically 512 or 768, to a much larger intermediate dimension, usually 40 is the model dimension, so 2048 or 3072. The max 0 applies the ReLU activation function, introducing crucial non-linearity. Then Womble by contracts back to the original model dimension. This expansion-contraction pattern serves multiple purposes. The larger intermediate dimension gives the network more computational capacity to process complex patterns. The non-linearity allows the model to learn complex functions that pure attention cannot capture. For data scientists, the FFN is where much of the model's thinking happens. While attention gathers relevant information from across the sequence, the FFN processes and transforms that information. In GPT-3, roughly 75% of the parameters are in these feed-forward layers, not in attention. This makes the FFN critical for the model's capacity to understand and generate complex language patterns. Now, let's assemble the complete transformer block architecture. Picture the data flow. Input vectors enter the block and immediately split into two paths. The main path goes through multi-head attention, which contextualizes each token based on its relationships with all other tokens. The attention output is then added to the original input via a residual connection and normalized through layer normalization. This is our first add and norm sublayer. The result flows into the position-wise feed-forward network where each token's representation is individually processed and transformed. Again, we apply a residual connection by adding the FFN input to its output, followed by another layer normalization, our second add-in norm sublayer. The final output becomes the input to the next transformer block. This two-sublayer structure, attention plus add-in norm, then FFN plus add-in norm, is the fundamental building block repeated throughout the entire model. GPT-4 stacks 96 of these blocks, each building increasingly abstract representations of the input. For data scientists, visualizing this flow helps debug model behavior and understand where different types of processing occur. The residual connections ensure stable gradient flow, while the normalization keeps values in reasonable ranges throughout the deep stack. We processed our input through multiple transformer blocks, creating highly contextualized vector representations that capture deep linguistic understanding. But we have a problem. The model has thought about the input, but it still speaks in the language of high-dimensional vectors. How do we translate these mathematical insights back into human-readable text? This final module covers the elegant solution, the output generation process that converts internal representations into probability distributions over our vocabulary. This is where the magic of text generation happens. Every word you've seen from ChatGPT, every response from Claude, every completion from Copilot, they all emerge from this mathematical process. We'll explore the linear projection that expands our final vectors to vocabulary size, the softmax function that creates probability distributions, and the autoregressive loop that generates coherent text one token at a time. By the end, you'll understand the complete journey from input text to generated response. The first step in output generation is the final linear projection layer. After processing through all transformer blocks, we have a vector of size D model, typically 768, 1024 or larger, representing the final contextualized understanding of our input. But to generate the next token, we need to compare this understanding against every possible token in our vocabulary. This requires expanding our demodel dimensional vector to vocabulary size dimensions, often 50,000 to 100,000 plus dimensions. The linear projection accomplishes this through a simple matrix multiplication, log its final vector time wave output is a learned weight matrix of size time model vocabulary size. Each element in the resulting logits vector represents the model's raw score for how likely that particular token should come next. For example, if token 1534 represents D, then logits 1534 contains the model's confidence that D should be the next word. These raw scores, called logits, aren't probabilities yet. They can be any real number, positive or negative. A high positive logit indicates strong confidence, while negative logits suggest the token is unlikely. For data scientists, understanding this projection is crucial because the output vocabulary size directly affects model memory requirements and computational cost during inference. Raw logits aren't directly useful. We need probabilities that sum to 1.0 and represent the model's confidence distribution across all possible next tokens. This is where the softmax function performs its final transformation. The softmax formula is softmax zz xp zz xp zg, where zz is the logit for token I and the denominator sums over all tokens in the vocabulary. Let's understand what this function does. The exponential function xp converts all logits to positive values. Even negative logits become small positive numbers. This ensures all probabilities are non-negative. The division by the sum of all exponentials normalizes the values so they sum to exactly 1.0, creating a valid probability distribution. Importantly, softmax preserves the relative ordering of logits while creating meaningful probability gaps. A logit of 10 versus 5 becomes a probability ratio of about 48,001 after softmax, clearly indicating the model's strong preference. For data scientists, softmax has crucial properties. It's differentiable, enabling gradient-based training, it amplifies differences between high and low scores, and it gracefully handles vocabulary sizes from thousands to hundreds of thousands. The temperature parameter can also be applied during softmax to control randomness. Higher temperatures create more uniform distributions, while lower temperatures create sharper, more confident predictions. Now we can complete the autoregressive generation loop, the process that enables coherent multi-token text generation. Here's how it works. Step 1. Provide the initial input sequence to the model. Step 2. Process through all transformer blocks to get contextualized representations. Step 3. Apply linear projection to get logits for all vocabulary tokens. Step 4. Apply softmax to convert logits into a probability distribution. Step 5. Sample from this distribution to select the next token. This could be the highest probability token, greedy sampling, or a random sample weighted by probabilities. Step 6. Append the selected token to the input sequence. Step 7. Repeat from step 2 with the expanded sequence. This loop continues until a stopping condition is met. Either a special end token is generated, a maximum length is reached, or the user stops generation. The autoregressive nature means each new token depends on all previous tokens in the sequence, enabling the model to maintain coherence and context across long generations. For data scientists, understanding this loop is crucial because it explains computational scaling. Each new token requires a full forward pass, memory requirements, storing the growing sequence, and why techniques like beam search or nucleus sampling can improve generation quality. This autoregressive process is what transforms a single prompt into the coherent, contextually appropriate responses that make modern AI assistants possible. We've successfully deconstructed the LLM from a mysterious black box into a series of understandable mathematical transformations. Let's trace the complete journey. Module 1 showed us input processing, how tokenization breaks text into subword units, embeddings capture semantic meaning in high-dimensional vectors, and positional encoding adds sequence information through sinusoidal functions. Module 2 revealed the attention mechanism, how query, key, and value vectors enable contextual understanding through the scale-product attention formula that revolutionized AI. Module 3 explored the transformer block, how attention combines with feed-forward networks, residual connections, and layer normalization to create deep trainable architectures. Module 4 completed the picture with output generation, how linear projections and softmax functions convert internal representations back to probability distributions over vocabulary tokens. You now understand the mathematical foundations that power every major LLM, from GPT to Claude to the models you'll build in your own research. This knowledge transforms you from a user of AI into a potential creator and innovator. The black box is now transparent, and the path to contribution is clear. Let's translate this theoretical knowledge into practical action with a concrete implementation roadmap. Your 30-day goal: read the foundational paper, Attention is All You Need, by Vaswani et al. You will now recognize every component we've discussed: the multi-head attention, positional encoding, and transformer blocks. This paper will solidify your understanding and introduce additional architectural details. Your 60-day goal: implement a simplified transformer block from scratch using PyTorch or TensorFlow. Start with the attention mechanism, add residual connections and layer normalization, then include the feed-forward network. This hands-on experience will deepen your intuition about how these components interact. Your 90-day goal: analyze the attention heads of a pre-trained model like BERT or GPT-2 on a task relevant to your work. Use tools like BERTFizz to visualize attention patterns and understand what linguistic relationships different heads have learned. This analysis will bridge theory with practical model interpretation. Each milestone builds your expertise systematically, from theoretical understanding to implementation experience to practical analysis. For data scientists serious about Gen AI research, this roadmap provides the foundation for contributing to cutting-edge developments in transformer architectures, attention mechanisms, and language model optimization. You now possess the foundational knowledge that separates AI users from AI creators. This mathematical understanding of transformer architectures is your entry point into the most exciting field in technology. But learning doesn't stop here. It accelerates. Explore advanced topics like mixture of experts architectures that scale models efficiently, different decoding strategies that improve generation quality, and model fine-tuning techniques that adapt pre-trained models to specific domains. Dive deeper with resources like the Illustrated Transformer for visual explanations, transformer circuits for mechanistic interpretability, and key academic papers that push the boundaries of what's possible. The field moves fast, but you now have the mathematical foundation to understand and contribute to every breakthrough. Whether you're building the next generation of language models, developing novel attention mechanisms, or applying transformers to new domains, you have the tools to make a meaningful impact. Your journey from user to creator starts now. The future of AI is waiting for your contributions.